All right, there is a rotational form of Newton's second law that we're going to be using a lot in this topic, and it looks a lot like the old one. Sum of the forces equals mass times acceleration. And if you just heard that, that's my son Max playing in the yard while I record this. So you might hear some yelling in the background. It's probably fine. So this is the linear form where a net force causes an acceleration, and an object's mass acts as a way to resist that acceleration. The rotational form looks like this. There's a net torque, and it will cause an angular acceleration. But the thing that resists an object's tendency to resist angular acceleration is not simply mass. Because if that mass is distributed differently, so the thing that resists angular acceleration instead of mass is called moment of inertia. And we're going to come back to this, but basically it depends on mass and the location of that mass relative to an axis. So an object can have different moments of inertia depending on what axis you're trying to rotate it around. If you think about like a football, when you throw a football and it has a nice spiral, that means that axis is the axis for that football that has the smallest moment of inertia. So we'll go further into moment of inertia later because we don't actually need it right now, because the problems we're about to work are all static equilibrium, which means the sum of the torques will equal I times 0. So we don't really even need to know how to calculate I right now, because all of our problems that we're about to work use the fact that the sum of the torques equals 0. Okay, so a simple statics problem looks something like this. Let's say there's this big beam, wooden beam, or plank, piece of wood, and it is sitting on some supports. And often supports look like little triangles, and these are just symbols. They could stand for anything. But when you see a support like this, the only thing this support can do to that wooden plank is push up. It's not actually attached. There's no pin holding it in place. So the only thing that these two supports could possibly do is push back up on that plank. Let's say the plank weighs 500 newtons, and there's a person standing on it, let's say 1 meter from this end, and let's say the whole thing is 5 meters long. So from the other end to the person, it's 4 meters. First thing you want to do in a statics problem is draw a diagram of the object, except now we're not drawing free body diagrams because we care about the body now. We care about where the forces are being applied because that will determine what the torque is. So for this object, you could just draw a simple line. The thing that's important is that there could be a reaction force. Let's say that's point A and that's point B. There could be a reaction force up on the plank from A. And there's also, there could be a reaction force up at B. And when you're drawing these reaction forces, we don't really know what they are yet. We just know that there could be one there. And then there's the person is exerting a downwards force onto the plank, and the plank is exerting an upwards force back onto the person. We don't really care about the person right now, so just draw the downwards force for the weight of the... Let's see, it looks like I never said what the person's weight was, so if it's a 50 kilogram person... I see it. If it's a 50 kilogram person, then that's another 500 Newton force right there. So the plank has a weight also of 500 newtons, and the place where you should draw weights is the center of mass of an object. Sometimes you'll see a little symbol. Oh, that's a bad symbol. Sometimes you'll see a little symbol that looks like this. That's the center of mass. You may not see the symbol. You may see the symbol. The center of mass is not always in the center of an object, but if the object is uniform and there's not more of it on that side and that side, then it probably is in the center of the object. In IB physics, most of the objects we see will be uniform and you'll be able to easily guess where the center of mass is. But you can pretend like that weight of the object acts as a single force at the location of the center of mass. And for those purposes, you'll get all the torque calculations correct. All right, it looks like we have all the forces drawn here. So if we know that it's in static equilibrium, that means there are no accelerations. So the thing you might want to be solving for here is maybe the problem asks you to find the support forces at A and B. In order to do that, we can use our old tool of sum of the forces equals mass times acceleration, but there's no acceleration, so sum of the forces is 0. There aren't any horizontal forces, there's only vertical forces. So I'm going to write a little up arrow here to indicate that I'm saying up is positive. And then when I do the sum of the forces, I'm going to have RA going up, RB going up, minus 500 newtons for the weight of the person, minus another 500 newtons for the weight of the plank. But we won't be able to get any further than saying that the sum of the two support forces is 1,000. We're stuck now. So this is where the torque form of Newton's second law comes in. Now we can say that the sum of the torques equals I times alpha, which is just going to be 0 because it's in static equilibrium. Over here I'm going to put a little clockwise symbol to indicate that that's positive for my sum. And then we just calculate the torque. Well, first, it's always important when you go to calculate torques that it's clear what point is going to act as your reference point or your axis of rotation. And in these torque problems, you'll see that if you pick the point cleverly, you can reduce the amount of work you have to do. So if I pick point A over here on the left, I'm going to write a little A right there to indicate that I'm summing the torques around point A. And if anyone comes behind me, they'll be able to do the same thing. But if I don't indicate where I'm summing the torques, it's going to be really hard to figure out just by looking at your work what point you picked. So if I choose point A, what torque does RA exert around point A? You could try using the R perpendicular times F form, but if you draw the line of action for RA, it goes through the axis of rotation. So there is no R perpendicular. R perpendicular is 0. When forces have a line of action that go through the axis of rotation, they're never going to exert a torque. So because I chose point A, the unknown force that's acting through point A doesn't actually exert any torque. That's the thing that lets you eliminate unknowns when you're solving these problems. Is when you pick a point and an unknown force acts through that point, you don't have to find that force anymore. Or if you need it, later there's going to be another way to find it, as we'll see. So that exerts no force. The first 500 Newton force is a meter from point A, and the next one, if this is in the middle and the plank is 5 meters long, then the next, that's going to be 2.5 meters from point A. So the person's weight on the plank will exert a negative torque, because if you imagine this force causing a rotation around point A, it's pushing down, so that would tend to rotate this clockwise, which is negative. So negative, the distance from this point is 1 meter, and then the force itself is 500 newtons. And if you wanted, it depends on which method you're using to calculate torque. But let's say you're using just the formula with sine theta. Theta here would be 90 degrees, because this would be the r vector, that would be the force vector. That's 90 degrees. So I don't even have to write it, but I will these first 2 times. The next force that causes a torque is the weight of the plank. It's 2.5 meters from the end. It's also going to be clockwise, so that's negative. So negative 2.5 meters times 500 newtons. And let's say here I use the r perpendicular times force version of calculating torque. If you draw the line of action of this force, the shortest distance between the axis of rotation, point A, and this line of action is 2.5 meters. That's because it's already perpendicular. You want water?
Yeah.
Okay, hold on. And then the last force that causes a torque is the reaction force at B. That will be a positive torque because it would rotate this whole plank counterclockwise, and it's 5 meters away. But we don't know what RB is. That's an unknown. All of those things added together will be 0. Now, do you see how we know all of these numbers except for RB? So we can go ahead and solve for RB. Okay, and if you do that, you get 350. RB equals 350 newtons. Now, there's different ways you could go back and figure out what RA is, but because I already used the old form of Newton's second law, I have a fast way of figuring out what RA is. RA will just be 1000 minus RB, because I already knew that. If you didn't already know that, another strategy that's fast is that you could redo this torque calculation, but choose point B as your axis of rotation. Then this force is the one that would not show up, and RA is the force that would show up, and you would be able to find it.